Today we are going to develop a linear model of the nonlinear dynamics of the synchronous machine. Actually, in previous video, I had talked about the dynamic characteristics of the synchronous machine that is connected to the grid. And when some disturbance is applied in the system, then the system will behave in some certain way, and after some time, the transient part can die out, and system may reach in another steady state condition, or maybe system could be unstable and fails, or some circuit breaker trip downs, or something can happen. Okay, so basically, what is linearization? Linearization is basically a process of developing the linear model of a nonlinear system. I mean, for a system, let's say, that is nonlinear in nature. It's some kind of a nonlinear graph. Okay, so my point of concern is something like this. Some point is like this. Okay, this may be x naught and y naught, and this is my operating point of at this moment. This is my operating point. So the basic idea of the developing linear model is to develop of some equation that will define the characteristics of the system around some very small area, or nearby the equilibrium point. So if I zoom out this point, this is some kind of this may be the actual dynamics kind of curve, and this line may be the linear model. This is the non-linear, this is the linear. Okay, so this curve at the for this part, we can represent by this line. Okay, this is the very basic principle of the linearization. Actually, any nonlinear dynamics can be represented in terms of the linear dynamics. The major advantage of the linear model is we can apply the classical control theories to design the controllers, or tuning the controller parameters, or some others. Okay, so this is the basic principle of the linearization. But in the context of the synchronous machine, we have set of differential equations that has to be linearized, and there may be the algebraic equations that comes from the load flows, and the dynamical equation that comes from the equivalent circuit of equivalent model of the synchronous machine. So in such context, how will develop the linear model? Okay, how will develop a linear model? For the simplicity, I asked to the this is Grok, and it says, first we have to understand the system, and these are our differential equation, set of differential equation. These are our set of the algebraic equation. Okay, and first we need some equilibrium point. These are equilibrium point, and after determine the equilibrium point, we use some perturbation. Perturbation means small deviation around the equilibrium point. I already mentioned here, this is the small deviation, this is the perturbation. Okay, this is delta x plus delta x. Okay, x plus delta x. So this is the small perturbation to develop the linear model of the system. Sorry. And after applying some perturbation, we do some Taylor expansion and calculate the Jacobian, and after developing the Jacobian individual set of differential equation and algebraic equation, we obtain the partial differentiation, and we obtain the small signal model, or the linear model. But there are differential and algebraic equations, so we can eliminate the algebraic part and develop a dynamical part only. And this is our equation, that is equivalent linear model of the system, that represents the overall dynamics of the synchronous machine around the equilibrium or operating equilibrium point. Okay, and you can calculate like this. So in programming, first, these are machine parameters, and in previous video I just solved the nonlinear solution. Okay, nonlinear solution. And currently the mechanical torque is 0.8, field is 1.2 pu, and grid voltage is 1, and synchronous speed is 1. So if I applied some if I solve the system of nonlinear equation for this input condition for zero initial condition, then for the speed we can update this kind of the curve. That is, synchronous machine will just pick up its speed and reach some steady state value. This is the steady state equilibrium value. Okay, 1 is the equilibrium point. You can see that the steady state value is like this: 1, speed is 1, angle is 0.86, and the transient internal voltage in d axis and q axis are like this. Okay, this is the just for the simplicity, you can understand the steady state value like this. But we can develop the steady state or equilibrium point by directly solving the set of algebraic and differential equations like this. Okay, we write the algebraic equation and differential equation like this, and use the and solve command of the simply, and we can solve the initial values. So I solve the initial values, and these are the equilibrium points. And you may have already noticed that the steady state values is equal to this equilibrium value. Now I want to add some perturbation. Okay, let's say I want to change the field by adding some 0.2 value extra. Previously it was 1.2. Now I want to add 0.2. The operator want to increase the excitation at some instant. Okay, the instant is let's say 70 seconds time. Now if we did that, the initial condition will be the initial steady state condition of the machine, and if we solve, then at the instant when the operator just turn or they raise the excitation, then the speed will slightly dips and pick up again. Okay, this is the transient part, and this is the some steady state point, and we can just plot for other variables also. Now this is the nonlinear solution. Okay, just integrating the set of differential equation by some numerical integrator, RK4 or Euler or something like that. But I want to linearize at some steady state point. And for linearization, I already mentioned from the gok.ai, I calculate the Jacobian matrix. I defined the differential equations. I defined the algebraic equations, and I calculate all the matrices that are required, and I calculate the A and B matrices here. So after getting A and B matrix here, this is the A and B matrix that represents the linear model of the system around that equilibrium point on which system is operating or the machine is operating. Now I add some perturbation, that is 0.2. okay, I add some perturbation, and the perturbation is added to the field. This was the initial value of the input, and this would be the final value of the input. So the change is delta. Okay, we'll talk about delta. Everything will be delta. I mean, the change in input will be delta u. Okay, we have to calculate everything in change, relative change. So the system is solved, the initial condition is made 0 about that equilibrium point, that is the 0 point, and how the system deviates from that equilibrium point, and this will be the solution. And you know, this was the initial condition in which the system was linearized, and after getting solution, we have to do that, we have to add that initial condition. This is the solution from the initial condition, and we have to add, and we solve for the zero initial condition, and we add the initial value. And if we do that, then we obtain the solution for the linear condition and the nonlinear condition. Here we can see that the linear solution and the nonlinear solution kind of try to match to each other, but it does not exactly matches due to the assumption that the Taylor expansion or in shortly I can say that we just ignore the higher order terms of the Taylor expansion. So this is why the nonlinear or linear model does not exactly fit it in a linear model, but still we can get lots of information about the system and in the linear model, which can be very helpful for developing the lots of controller tuning or designing the power system stabilizer or maybe ABR or governor or something like that. Okay, this is the very basic demonstration for the importance of the linearization and importance of, or the process of the linearization of the nonlinear system of the synchronous machine. So thank you for this, and I think I will do this much for the dynamical system for. Okay, thank you.